Let's talk about complex exponentials. Complex exponentials are useful because they're going to give us an alternative method for working with cosines that's actually going to be a lot easier to use. So let's start by thinking about our generic complex number x. So as hopefully everyone knows, we can conceptualize complex numbers in either rectangular form or polar form. And let's draw some complex number x here. So that complex number x has got a real part and an imaginary part, but alternatively we can consider it as having, if we think about it in polar form, we can say that it has a magnitude m and a phase theta. So in other words, we can say that x equals, expressed in polar form, it'll be m e to the j theta, and expressed in rectangular form, it'll be m cosine theta plus j m sine theta, where j is the square root of -1. Now, alternately, we can consider a different point, which we're going to call x conjugate. Now, there's two ways to define a conjugate. In rectangular form, it's something that has the same magnitude but opposite phase. And that's in polar form. In rectangular form, it's the same real part but opposite imaginary part. So let's say that x conjugate is going to be m e to the minus j theta equals m cosine minus theta plus j m sine of minus theta. Now, as it turns out, cosine is an even function. So if I were to draw a generic cosine, you would see something that maybe starts out looking like this. That's not a very good cosine, but you get the idea. And in doing so, you can see that cosine of theta and cosine of negative theta are the same, right? And that's because cosine is an even function. So in other words, cosine of negative theta is going to equal cosine of theta. Now conversely, sine is an odd function. So if we were to draw ourselves a generic sine function, that's a little better, not much. We'll see that sine of theta and sine of negative theta are equal and opposite. So in other words, sine of negative theta is the same as negative sine of positive theta, and that's just because that's an odd function. So putting all those pieces of information together, we can rewrite our complex exponential for the conjugate as m cosine theta minus jm sine theta. Let's try that again. Sine theta. Much better. Now, all this leaves us with two equations. We have equation number 1 and we have equation number 2. If we take equation number 1 and add it to equation, happens. So let's add the left side of the equation together. We get m e to the j theta plus m e to the minus j theta. And on the right hand side of the equation, the two cosines add together. So that gives us 2m cosine theta. And then the sines are, not that one. That's equation 1. And this is equation 2. They're equal and opposite, so they cancel each other out to 0. So we just get left with this. And rewriting that slightly, we get cosine of theta equals, let's see if we can do this right on the first try, 1/2 e to the j theta plus 1/2 e to the minus j theta. Now, we can actually do the same thing for subtracting 1 and 2. So if we take equation 1 minus equation 2, that leaves us with something that's also very useful. M e to the j theta minus m e to the minus j theta equals 2jm sine theta. So in this case, it's the cosines that subtract out. And that tells us that sine theta is going to equal 1/2j e to the j theta minus 1/2j e to the minus j theta. So these are both fairly useful expressions that will come up with some frequency in our study of signals. Now, we know that most cosines aren't just cosine theta. We know that the generic form of a cosine is k cosine some frequency omega t plus a phase shift phi. So let's see if we can figure out how to rewrite that as a complex exponential. So all I'm going to do is I'm going to take the entire contents of my parentheses and I'm going to substitute them in for theta. And I'm going to scale the whole thing by k. So when I do that, I'm going to get k over 2 e to the j omega t plus phi. So that's the first complex exponential, plus k over 2 e to the minus j omega t plus phi. And that's pretty ugly, so I'm going to kind of tidy this up a little bit. I'm going to rewrite that as k over 2 e to the j phi times e to the j omega t. And the reason I can do that is that the exponents add. So if you see here my two e's, because it's the same base, the exponents add. Okay, so plus k over 2 e to the minus j phi times e to the minus j omega t. Now you have something pretty interesting going on here. We have these two e to the j omega t and e to the negative j omega t terms. Those are functions of time. Okay? They're complex functions, but they're functions. And next to them, you have these other two terms that are not functions. They are constants. That's why I've grouped them together like that. They are constants, or you could think of them as coefficients. We're going to see a lot of them in this study of signals. We're going to see this pattern a lot. In fact, we're going to see this pattern so much that I'm going to call this constant A. Okay, it's a complex number with magnitude k over 2 and phase angle phi. Now, if you look at this constant over here, it's interesting. It's got the same magnitude k over 2, but it's got the opposite phase angle. And because of that, that's actually going to be a conjugate. So putting this all together, we can decide that an alternate representation of our cosine will be as follows. We can say that is equal to a e to the j omega t plus a conjugate e to the negative j omega t, subject to the important constraint that a equals k over 2 e to the j phi. So let's do an example. Let's suppose that x of t equals something like 0.3 cosine, I don't know, 2 pi 227t plus 0.3 pi. And I say express that as a sum of complex exponentials. Well, just by pattern matching, you should be able to say that equals a e to the j 2 pi, sorry, that should have been 227t plus a conjugate e to the minus j 2 pi 227t, subject to the constraint that a equals k over 2 e to the j 0.3 pi. And that's it. Now, if you want to test yourself to see if you really know what's going on, try the following. Suppose I give you some function y of t equals a e to the j 250t plus a conjugate e to the minus j 250t, subject to the constraint that a equals 0.7 e to the minus j, I don't know, 0.8. Okay, so plot that function. So if you understand this, you should be able to plot the function y of t. And to give you a hint, the first step is to convert y of t into a cosine, which you should be able to do using the steps that we followed in this video. And then once you have the cosine, you should be able to use the magnitude, the coefficient, the frequency, and the phase to make a plot of the function.